Hi there, my name is Eric Casey and I'd like to present to you my submission for the 2018 Queen's University International Innovation Challenge. I've been looking for a reason to jump into traffic data and simulation for a long time and have only scratched the surface so far. Recent buzz about driverless vehicles in Toronto has inspired me to combine the topics. My experience is primarily in digital marketing, my interests lie in entrepreneurship and tech, and my education is primarily in business. I'm currently enrolled in the Queen's MMA program and expect to graduate in 2019. In 2017, Toronto had the 6th worst commute in the world according to the INRIX Global Traffic Scorecard. It was estimated that commuters in Toronto waste about 15 lifetimes each year because of congestion. Recent years have seen an increase in fatalities on the road as well as increased danger to cyclists and pedestrians. 66% of all recorded accidents happen at intersections, and 45% of those are in the intersection. Speaking of intersections, Toronto has an open data portal with details for all 2,400 traffic lights in the city. The average age of each lighting system is 40 years, and only 22 are dynamically timed. This chart shows the total number of fatal road accidents in Toronto from 2008 to 2017. As you can see, recent years have seen an unfortunate increase in traffic fatalities. Vision Zero is a data-driven road safety improvement concept initially adopted by Sweden in 1997. Toronto's current Vision Zero plan is a 5-year, $80 million project focused on 50 directives with the goal of zero traffic fatalities as soon as possible. $22 million of this budget is to be used for intersection redesign and traffic light retiming. The traffic signal data I acquired for this project doesn't include signal timing or intersection dimensions, which would have been useful in simulation. This is because the city offers that data for sale to private business at $100 per signal time and $270 per intersection drawing, which amounts to about $800,000 in value for all 2,400 traffic lights. Personally, I think it's worth much more in the hands of the public, and I doubt it sells very well. I just hope the signal timing data was made available free of charge to the competitors in this summer's Toronto Vision Zero Challenge that cost $120,000 to run. This graph shows the total number of accidents by year for a 10-year period and a 17-year forecast before the number of accidents reaches zero. This data is openly provided by the Toronto Police Public Safety Open Data Portal and includes 12,000 accidents from 2007 to 2017, with some missing data in 2007. I chose to use the number of accidents with certain characteristics for my analysis for a far more reasonable sample size of 12,000 accidents rather than the 600 fatal accidents in the dataset, and assumed a 5% fatality rate. In my early exploration of this data, I found that I could predict the fatality of an accident with 95% confidence. After investigating the most significant variables, I discovered that they included speeding and driver inattentiveness. Dr. Nicholas Ward, director of the Center for Health and Safety Culture at Montana State University, uses a similar linear projection for his planning, which as of 2018 sets target zero for Washington State at 2030. My projections use all road accidents rather than just those that are fatal, but it's interesting to note that Washington State has also seen a recent spike in traffic fatalities. Each line of this graph represents the frequency of several accident characteristics between 2007 and 2017, as well as projections into the same 17-year period. As you can see, most characteristics converge or fall below zero between 2024 and 2034. The ones that don't cross zero are fatal, cyclist, pedestrian, and distracted driving. For my final prediction at the end of the video, we'll analyze what the state of affairs would look like in 2025 considering a number of factors. I hypothesize that using existing infrastructure and technology, the people and City of Toronto can prepare for automated vehicles on our roads using community-generated machine learning training data and, through early adoption of automated vehicle technology, achieve target zero before 2034. This project assumes a few things. 1. On-demand vehicle fleets will continue to grow. This first chart shows search trends related to taxi and ride-sharing services and shows that ride-sharing is on the rise while taxi has been falling in recent years. 2. Automated vehicle interest and sales will continue to grow. This second chart shows search trend data for topics revolving around driverless vehicles. And 3. Non-conservative adoption, meaning that the city will adopt automated vehicles and there will be strong growth in their demand, which we'll get back to at the end of the video. Now there are 6 levels of vehicle automation. Level 0 to 2 we have on the road now. The Model T at level 0, a modern minivan with emergency braking would fall into level 1, and a Tesla with autopilot often falls into level 2. For the purposes of this video, I will primarily consider levels 3 to 5, where we'll find Uber and Waymo's automated cars, the Google driverless car, Herbie, Christine, and Kit from Knight Rider. The automated cars of today are mostly existing road-legal cars that are retrofitted with LiDAR and radar units for detecting range, cameras to identify objects in their environment, and a main computer. The 2 solutions I'd like to propose aim to first pre-train automated cars to recognize their surroundings in Toronto, then, in the early stages of adoption, a device used to communicate with its surroundings. Solution 1 is a Google Maps-based app full of Toronto and Geotab's open data, and is used to share information and generate community-driven road etiquette to be used for pre-training automated vehicles in simulation, as well as improving their computer vision model specificity in local object detection. Solution 2 is a low-cost secondary compute device used for communication with the vehicle's surroundings and infrastructure, with the purpose of reducing road incidents, relieving congestion, and collecting valuable infrastructure information. Research shows that traffic safety measures like speed bumps don't actually change driver behavior. A driver will slow for a speed bump, but it doesn't mean they'll drive any safer when there are no speed bumps. This has led researchers to believe that changing societal norms is the most effective way to change behavior. This is evident in my research as the frequency of alcohol-related accidents is falling faster than any other accident characteristics. The web app I've created aims to generate a feedback loop that can help optimize public spending on intersection redesign, as well as produce valuable information used in computer vision training. 2,400 traffic lights, 250 traffic cameras, and 12,000 accidents, formatted in keyhole markup format and connected in real time to the Google Maps Traffic API. This app allows a user to explore Toronto's open data and submit feedback in a number of ways. The payload of the user's feedback can include text, dash camera footage, coordinates, and polyline drawings over the map. These polylines, paired with a binary good-bad rating or Net Promoter Score, could help the city isolate problem intersections and behaviors that frustrate the public by categorizing certain road maneuvers as safe, unsafe, or inefficient. The most useful output from this app is what can be used for computer vision. A custom image capture tool generated from user-submitted and verified dash camera footage can help label images of city infrastructure. These images can be used to generate high-quality hard cascades and other modules for computer vision object detection. This could be used to detect humans, cyclists, lights, signs, and more, ultimately generating dev kits for automated vehicle producers to use to make their computer vision models more accurate for Toronto driving. The endgame, of course, is a traffic system like the one in the 2002 film Minority Report, where everyone can get anywhere using trustworthy technology and traffic networks that yield maximum throughput 24/7. What I've found to have often been overlooked in traffic simulations like this one is that between now and then, there will be a combination of both driven and driverless vehicles sharing the road. In the long run, automated cars are going to need to be extremely good at understanding their environment and communicating with other vehicles. But in the interim, there will be a blend of automation levels on the road, and communication between these automated vehicles and the humans they share the road with will be paramount. This is a complexity I hope to expand on using this simple micro simulation. It assumes a half-second lag time for the red, human-driven cars to account for texting and courtesy, and a very small lag time for the automated blue cars. So the 10th blue car can advance at almost the same rate as the first, knowing that all vehicles ahead of it were automated, planned to accelerate, and the path was clear. In this simulation, the blue automated cars spend 10.5 seconds moving, while the red driven cars spend 15 seconds moving. This is the kind of high-efficiency communication that my second solution hopes to facilitate in the early stages of automated vehicle adoption, with the benefit of also reducing traffic congestion. My second solution I'm calling the Keystone device, which I believe would fit well in the Geotab marketplace. It's a triangular device mounted on the front and back of an automated vehicle used for normal signaling and braking, but also for alternate functions like emergency service alerts, daisy chains, detour lead cars, and vehicle-to-infrastructure communication. The primary goal is to break ground on two-way vehicle-to-vehicle and vehicle-to-human communication, as well as collect and leverage the increasing amount of visible and invisible information being transferred on the road. I've created a list of about 10 alternate functions that can be added to the device as needed in order to reduce the likelihood of the Hicks-Hyman law negatively impacting the whole traffic system. That is, that too many lights would be confusing and cause more accidents. Another option is simply conditional use. I have a working prototype of the device in my living room made from lighting decorations, cardboard, tape, and a coat hanger. The next prototype would be smaller and costlier, but would come much closer to a final product. The device has 3 triangular indicator lights, a red continuous outline that replaces the brake light, a speaker and mic, an internal computer for vehicle-to-infrastructure edge computing, and an LED matrix for generating QR codes for vehicles of varying automation to speak with each other. One of the most powerful features of the device is the central triangle, which allows the car to display QR codes that can be read by the cars around it, for the purposes of communicating information like the car's intentions and route. This could be used both at intersections as well as for highway convoys of vehicles composed of cars with varying levels of automation. This on-screen explanation shows how we can enable the type of vehicle-to-vehicle communication needed to make the lane with the daisy-chained blue cars from my micro simulation a reality. The second function is to warn the drivers around it that there are emergency services vehicles coming that might be out of earshot or sight in hopes of reducing the time it takes for an ambulance to reach the scene of an accident. The third function is a black box edge computer for collecting data from other vehicles that have opted into sharing, for collecting crash footage to be sent to the involved parties and their insurance companies for review. The detour leader function will help load balance certain routes in the city in order to keep things moving. Disability assistance could be made available at any intersection in which an automated vehicle is in front. Finally, since cyclists and pedestrians are at high risk on roadways, they may be the best road users to give rewards to automated vehicles using vocal commands like GoodBot for reinforcement training and competition. In review, we learned that Toronto's traffic system is slow and deadly due to congestion and human error. I hypothesized that automated cars may be our solution to achieving 0 deaths on the road before 2034. I presented my assumptions about the future of transportation and automation. My first solution, a public terminal for infrastructure feedback and machine learning training material, and my second solution, the Keystone device for improved road communication. I would like to close by bringing back the histogram of Toronto's car accidents. In this graph, the orange and green areas in the background represent the percentage of automated vehicle adoption versus regular cars and shows aggressive adoption starting with a similar initial fleet to that of Phoenix, Arizona, with 600 cars now in 2018 and a 200% annual growth rate. The green and blue lines represent the projected number of accidents given the status quo in blue and automated vehicle adoption in green. The green line takes into account accident types with characteristics like speeding, aggravated driving, and driver inattentiveness, and assumes that an automated vehicle could avoid 90% of those accident types. There are certainly more accident types present in this dataset that an automated vehicle could avoid, but the 3 characteristics used are most clearly avoidable and most significant when predicting the fatality of an accident. In 2025, where the green line's rate of change decreases, there are 200 total accidents, while our status quo line shows about 500 accidents. If we assume the 5% fatality rate, we can estimate about 10 fatalities in that year of adoption, compared to 25 without adoption. That's 15 fatalities avoided in 2025, and in total, 4,200 accidents and 200 deaths could be avoided between now and 2034. To be thorough, this second graph shows a linear growth rate to 95% automated vehicles in 2034. As you can see, the rate of automated vehicle accident avoidance over time is less extreme than the previous chart, but in 2025, I predict 375 total accidents and 19 fatalities, still 6 lower than the status quo. Between now and the final presentations in Toronto, I plan to first break ground on a Raspberry Pi-based prototype of the Keystone device, perform a more detailed cost and return analysis, and apply learnings from a number of research papers about traffic flow theory. Then, I plan to solidify my analysis by scaling my micro-simulation and app, training a computer vision model to recognize Toronto's infrastructure, and gain access to some full 3-axis accelerometer data in an attempt to reverse engineer the city's traffic signal timing schedule and measurement data. I've also sought out a number of industry professionals I hope to interface with in the coming weeks. I would like to thank you for listening and to the organizers for facilitating the challenge. As one man, I could only get so far with my analysis, but given part of the month of November to prepare, I hope to have included more of Geotab's data for use in my simulation, as well as work on a physical prototype of the Keystone device. Thanks again.